In this video, I'm going to be talking about how to solve a two-dimensional collision problem using the conservation of momentum. So the only difference between a 1D and 2D collision is a lot more organization and a little bit of trig. So we're going to have to use some trig so that we can use these angles and then find some x and y components. And really the idea of solving for the momentum, velocities, or angles is kind of all the same for any type of collision type problem, which is taking a look at the momentum of everything before the collision and that being equal to everything after the collision based on the conservation of momentum. But we're going to make sure we break up stuff into horizontal components, which I'll call the x component, and vertical components, which I will call the y component. Okay, so if we're taking a look at our scenario, we have a 2 kilogram ball coming in this way, a 3 kilogram ball coming in this way, and then afterwards our 3 kilogram ball bounces back at 1 meter per second, 10 degrees above the horizontal. So our question is basically, what happens to our 2 kilogram ball? We'll go ahead and call it VF. And then what is the final angle that it bounces off at? So it seems like there's a lot of information missing there. So this is definitely going to be slightly time consuming, but once you get the hang of it, the idea of it is not that complex. So the first thing we're going to do is we are going to keep in mind that everything going to the right, I'm going to call positive, and everything going to the left, I'm going to call negative. Anything going up, I'm going to call positive, and everything going down, I'm going to call negative. Okay, so when I draw my velocity vectors, I'm going to make sure I follow those rules, which is basically if I have anything to the left or down, I'm going to immediately add a negative sign next to it. Okay, so the first step is I'm going to draw 3 right triangles. So I'm going to pull this 4 meter per second velocity vector. I'm going to redraw it up here so I have plenty of room. Okay, I'm going to draw the components tip to tail. I'm going to go down and to the right. And then I have my 20-degree angle. Right over here. And then for my second triangle, I'm going to pull this one over here. I have 2 meters per second up and over this way. My angle is right here, and then my velocity vectors are going to go up and over to the left. So what I'm going to do now is I'm going to use sine and cosine, and the sine is going to be opposite of my angle on both of these, and which is going to give me my vertical component, and it's going to be sine is opposite over hypotenuse, so I get to use my hypotenuse of 4 and 2. And then for cosine, cosine is the adjacent side next to my angle, which is over here and over here, so cosine is going to give me my vertical components. Okay, so let me go ahead and solve for my components, and then we'll get back to the problem solving. Okay, so I went ahead and used my trig functions. I used the sine of the angle to find my my vertical components, and I made sure this one is negative because it's going down. This one over here is going up, so I got 1 meter per second, and then I went ahead and pulled my triangle from after the collision. That's going 1 meters per second this way. Everything is to the right and up, so I left everything positive. Okay, so what I'm going to do is right now I'm just going to focus on the x component. So I'm only going to concentrate on my x components, which are right here, and right here. And I'm going to set up my momentum before and after the collision. So I went ahead and used my momentum formula of mass times velocity, only using the x components at this point, and I did the mv for both things before the collision and then the mv of everything after the collision. And then after just kind of finding the product of these numbers here, you would do a little bit of basic algebra, and then you find out it is negative 0.61 kilogram meters per second equals 2 kilograms times VFX. So if I go ahead and divide both sides by 2, then I get a VFX of negative 0.305 meters per second. Okay, so what I'm going to do next is I'm going to do the same thing. I'm going to use mass times velocity of everything before and after the collision, but now I'm just going to use the vertical y components. All right, so same thing. I went ahead and plugged in everything I knew for the momentum before and after the collision, and the only thing I'm missing is my final y component of my 2 kilogram mass. And again, I just did some basic algebra. I multiplied these two and these two, summed them up, and then I found the product of these two, subtracted it from both sides, and then I got negative 0.25 kilogram meters per second, and that equals 2 kilograms times my VFY. And then again, I divided both sides by 2. And then I got a VFY of negative 0.125 meters per second. Now what I'm going to do is I'm going to take my x and y components I just solved for right here and right here and piece together my final triangle. So I have an x component that's negative, and remember, negative is to the left. So I have negative 0.305 meters per second. And then we always go tip to tail when adding vectors. So at the end of this tip, I'm going to add the tail, the bottom of my vector. And then that one is negative also. So negative means down in the vertical direction. So this one is going to be negative 0.125. My final answer is going to be the hypotenuse of that triangle. So I can go ahead and use Pythagorean theorem, which is a squared plus b squared equals c squared. So I'm going to square negative 0.305. I'm going to add it to the square of negative 0.125, and then eventually square root it. And it's going to leave me with an answer of 0.33 meters per second as my final velocity of the 2 kilogram object. So we want to find the final velocity, and also we want to find the angle at which it bounced off at. So I'm looking for this theta over here. So what I'm going to do is if I'm solving for a value involving a triangle, what I'll typically try to do is I'll try to use my original value. So my original values was this red one and this black one over here. I'll leave the blue one out for now, but you can use any two of your three sides. So I'm going to use the inverse tangent, and then tangent is opposite, which is the 0.125, negative 0.125 over the adjacent. And when I put in the inverse tangent, I'll have to slide that down over here. Inverse tangent of negative 0.125 over negative 0.305. That will give me my final angle of 22.29 degrees. And this is below the horizontal going back in this direction. So to sum things up, what you want to do is you want to take every velocity vector you have in the original problem and break it up into right triangles. And it's very important that you want to make sure you make every component as a vector. So then if it's down, you have a negative along with it. And if it's back the other direction, which I call to the left, you also add a negative along with it as well. Then you just do the mass times velocity of everything before and after the collision, but you have to first focus on one component at a time. So I just did strictly the X component first in this chunk over here, and then I did strictly the Y component in my second chunk over here. And then finally, when you want to finish off and find a final velocity, you piece together your components of the triangle here and here, and then your final velocity will be the hypotenuse of that triangle. And if you need to solve for a theta, the angle that it bounces off at, you can use the inverse of some kind of trig function. I chose to use the inverse tangent and use the opposite over the adjacent side, and I got my angle of 22.29 degrees. So I hope that was helpful in helping you set up, organize, and solve for a final velocity and an angle for a two-dimensional collision problem. Thank you for watching and listening.